Welcome. This is the Cisco CCNA ENSA, also known as the Enterprise Networking Security and Automation course. This course focuses on the CCNA version 7 curriculum. This is course 3 of 3. Now we have again our OSPF packets. We talked about the hello packet, the database description, link state request, update, and acknowledgement. Here's where we go a little bit more in depth. Generically, the hello packet will be used to discover neighbors and build adjacencies. The DBD will check for database synchronization. The LSRs will request specific information. The LSUs will send specific requests. The LSAs will acknowledge the other packet types. Again, the LSUs will have different types. The different LSAs will also have different types. Again, this is getting outside what you'd normally be needing for the CCNA. This is more CCNP, understanding the types of LSAs. This is more just information for you to have. LSUs are used to forward OSPF routing updates. An LSU packet can contain 11 different types of LSAs. LSUs and LSAs are often used interchangeably, but the correct hierarchy is an LSU packet contains LSA messages. And again, there are 11 different types of LSAs. Common LSAs, LSA 1 is a router LSA. 2 is a checksum for database. 3 or 4 is summarization of LSAs. 5 is the autonomous system external LSAs. 6 is a multicast OSPF LSA. 7 is a defined not so stubby area, and so forth. Again, outside the scope of this exam, this is more just FYI, so that you understand there is a process for the 11 LSAs. The OSPF Type 1 packet, the hello packet, are used to discover OSPF neighbors, advertise parameters, and elect a designated router, master router, and a backup designated router. So a designated router, DR, and a BDR on multi-access networks like Ethernet. Point-to-point links do not require a designated router or a backup designated router, but they may happen. OSPF has its own packet header, and it will have things like its router ID, its area ID, if there's authentication, the hello intervals. It will also have the designated router address and the backup designated router, as well as a list of neighbors. OSPF operations. We have 7 states of OSPF. There actually is no video for this. I don't know why it says video. So there are 7 main states: the down state, the initiate state, the two-way, the X-start, the exchange, loading, and full state. The down state, there is the initial default state. No help. Basically, the router just turns on. There is no hello packet received, so it's down. The router will then send hello packets, and it will transition to an initiate state. The initiate state basically is when you receive a hello packet from your neighbors. They contain the router ID of the sending router, and this will transition to a two-way state. Before it transitions, it may send an acknowledgement to verify the hello packets. The two-way state allows for communication between two routers bidirectionally, assuming a multi-access link like Ethernet, and they will start electing a designated router and a backup designated router. After they designate a designated router, they will transition to a two-state the two-state will transition to a X-start state method. And that XStart state method will be, the two routers will decide which router will initiate the DBD packet exchange. Again, that's the database. And will then decide upon the initiating BDB packet and the sequence number. They will then exchange information. So the routers exchanging the different database packets will be an exchange state. If additional routing information is required, then they will transition to a loading state after the exchange. If the exchange doesn't need additional information, it will transition to a full state. The loading state will send additional LSRs and LSUs to gain the additional information, and then it will run through the SPF algorithm again before transitioning to a full state. Again, a full state is when the link state database of the router is fully synchronized with all other routers in that area. And that process is how OSPF actually does its convergence throughout the area. So how do we establish a neighbor adjacency? So to determine if there is a neighbor on the link, the routers will send a router ID out all of the OSPF enabled interfaces using a multicast address. The multicast address 224.0.0.5 is basically used to send out an OSPF v2 packet out those interfaces. The OSPF router ID is used by the OSPF process to uniquely identify each router in the area. The ID is a 32-bit number formatted like an IPv4 address, but is assigned uniquely to each of the devices. You'll notice in the Cisco material, we keep them very simple: 1111, 2222, 3333, and so forth. In the real world, you'll have a documented network map, and you'd have the IDs laid out appropriately. When a neighboring OSPF-enabled router will receive a hello packet, it will look at the router ID, and if it's not within the neighborhood list, the receiving router will attempt to establish a new adjacency. The routers have to have adjacencies formed to be able to share information. There are a few different steps when we are looking at forming those adjacencies. Down to the initiate state, looking at OSPF v2. Basically, OSPF 2 is enabled on the interface. The transition from down to the initiate state will start sending once there's a hello packet on a interface. If there is no hello packet sent or received, it will not be able to discover neighbors. That hello packet is what's used to discover those neighbors. That will transition to an initiate state once the neighbor router receives the hello. So if we have router 1 learning about router 2, router 1 will send router 2 a hello packet. Router 2 will transition to an initiate state because it received a hello packet from R1 containing R1's router ID. R1 will then receive R2's hello packet and will notice the message will contain the router 1 ID in the list of information that R2's neighbors has. So now R1 will add R2's router ID to the neighbored list and will transition to a two-way state. If R1 and R2 are connected with a point-to-point, they transition to a XStart. Realistically, that's only used for point-to-point. If R1 and R2 are connected over a Ethernet, they will start forming a designate route and a backup designate route election, seeing who will become the master. The DR and BDR elections occur where the router with the highest router ID or the highest priority is elected as the designated router. The second highest will become the backup designated router. Again, here we're looking at the highest router ID will become the designated router or master. After the two-way state is enabled, the router will transition to a database synchronous state. Basically, this is where there are 3 steps that will occur to actually transition and sync database information. Basically, first, the first router will, the highest router ID, whatever the master router is, it will send the database DVD first. They will exchange DVDs as many times as needed to convey the appropriate updated information within the database. The other routers must then acknowledge each DVD with a LS acknowledgement packet. They will then send all slaves routers will send a LSR to each other, collecting the DVD information and storing it locally. As information is found to be missing, it will send up LSUs as a update request. And again, acknowledgement sent once all the information is then brought together. After all LSRs have been exchanged and satisfied, the routers are considered synchronized in a full state, and then there might be a update sent if there is any changing information. If not, every 30 minutes just to verify. This is when we would say that it is converged. All routers have all information on all other routers. So a question that I often get is, why have DRs? Why have that designated router? Why have that master? So when we're dealing with a multi-access network, they can create challenges for OSPF regarding the flooding of LSAs. The creation of those multiple adjacencies can cause issues. So Ethernet networks could potentially interconnect many OSPF routers over a common link, creating adjacencies where every router would lead to an excessive number of LSA exchanges, basically flooding the adjacencies. So a common formula is the number of adjacencies is equal to n, which is the number of routers, times n minus 1, all divided by 2. There are 5 routers, so you can actually have 5 times 4, that's 20, we divided that by 2. That means there are 10 adjacencies. This flooding can be very excessive. So, with a DR, we can control some of that flooding. So, LSA flooding with a DR, as increasing the numbers of routers on a multi-access network also increases the number of LSA exchanges between the router, the flooding then also increases. So if every router in a multi-access network had to flood with acknowledgements, you would start seeing a flood of those updates, and that uses bandwidth, and that would just create issues. So OSPF elects a DR. The DR will be used to collect and will also be used as a distribution point for LSAs. Basically, it will be sending and receiving them. The backup DR is also elected in case of a DR failure. All other routers will become DR others. Basically a third option. Basically, if the DR fails, the BDR becomes primary, and then they'll hold another election for a new BDR. The BDR is the only used for dissemination of LSAs. The router will still use the best next hop router indicated in the routing table, but the BR will actually be used to disseminate the router updates that will be used. And that is it for this module. If you got any questions or concerns, please reach out. Thank you.